Hi everyone. So today I'm going to talk about Cisco ASA firewalls and the story of journey, how I found a bug and how I exploited it. So I'm Cedric, working at HCC Group, doing vulnerability research, exploit development, and reverse engineering. And basically my main goal is to help the pen test team, because we have quite a huge pen test team, to basically weaponize exploit, so we can basically demonstrate vulnerabilities to clients, say, okay, you need to patch, basically. So I basically ported existing exploits focusing on ASA and started to do some fuzzing, and I found a pre-auth vulnerability on Cisco ASA firewalls. So today we're going to talk about that. And the idea was to prove remote code execution. So it's been patched now. There's been a lot of noise around this vulnerability. So I'm going to explain. First thing is, this bug is not in IKV1. The bug I found was originally found in WebVPN, but I've used IKV1 as a helper to prove remote code execution. So again, the bug is not in IKV1. So a little bit of context. What is a Cisco ASA firewall? So basically, if you use a VPN to connect to your company, which mostly you probably do, you probably have a Cisco ASA. So you have other manufacturers like Juniper or whatever, but it's basically the entry point to your enterprise. And the other thing to know also is that ASA is different from iOS. It's very confusing because they both have the same interface, the same command line interface, which is a Cisco shell, but they are different internally, and it's very important for exploitation because it means you have different constraints. So iOS is like a proprietary operating system. I'm not an expert on iOS, but I know it's mostly MIPS or PowerPC, but I've been mostly focusing on ASA. That's what we're going to talk about. ASA is Linux-based. So it's basically a Linux, like any Linux, normal Linux, with one single binary of 40 megabytes, and called Lina, and that contains everything. And because we're talking about router, it contains the actual network stack, meaning if you're on Linux, you don't have any network. It's the actual Lina battery that gives you this network and does everything. It's also interesting to know that it's x86 or 64 equivalent. So if you're used to that on the desktop, that's what you have in this router. So this is what we have, for example, some devices, different size, different model, but they all run the same kind of operating system. So I brought one. This is the one on the top. So this is the smallest one, the ASA 5505, and then you have more better one. So a little bit about the disclosure timeline, because it's a little bit confusing. There has been one advisory, then there's been another advisory. So what it is about? Basically, in October, I reported the vulnerability to Cisco, and they were able to replicate the issue. And I told them, okay, I'm going to talk about it next year. Is it okay? And we agreed. We're not going to release it before February, and they're going to release the advisory at the end of January. That's fine. And then early January, luckily, we discovered that actually the patches already existed. So that's interesting because I have 3 tables, and the first one on the left is basically my analysis. So when I realized that it was patched in early January, I checked all the versions after getting all the firmware, because the firmware are not available on the internet, so if you don't have a Cisco account, so that's another story. But once you have all the firmware, test them all and realize, okay, for example, 9.1, the 9.1.7.20 patched the vulnerability. So you have this system of branches I'm going to talk about just after, but each branch lives in parallel, and basically you need different patch for each branch. So then, at the end of January, like what was agreed, they released an advisory, and the patch were already existing since November, but they make it public, basically. And then I do my presentation at Recon, 5 of February, and the same day, I realized just watching on the internet that actually they updated their advisory, and the bug actually impacts other attack vectors. So what it is about? The interesting thing is, in the first advisory they released at the end of January, you can see on the second table that the version are very similar to the one I had tested early January, which makes sense, except one, which is 991. I had tested that was patched for me, at least for my proof of concept. But in their case, they say it's 9912. And what was interesting at that time is 9912 wasn't available. So that was quite weird. People were going crazy on the internet saying, oh, it's a huge bug, but the patch is not available. And actually, it all made sense when they actually released the second advisory, at least for me. Because basically, they probably realized that it was not totally fixed, and they said that it would be fixed in 9912, but it wasn't available at that time, and they also patched the same bug in all other branches. At least that's my assumption. So in the second advisory, they released an update for each branch that patched the actual bug. So that patched the actual bug, but also the other attack vectors. So to summarize, I found the initial vulnerability in WebVPN SSL, but actually it impacts the XML parser. I'm going to talk about it today. And originally, in the advisory, they said it's WebVPN SSL, but now they changed it to XML parser because it impacts other protocols that use the same XML parser. So originally, it was all the Cisco ASA that are on this list, except the new one, Firepower, that probably have some attack vectors that weren't WebVPN. I haven't checked, but that's my guess. And on the right, all the actual attack vectors. So the only one I had found, basically, kind of, is the AnyConnect and clientless SSL VPN that were basically the SSL VPN that I've used to exploit the bug. But all the other attack vectors are either local or remote, like the IKE v2 one, but some of them are local, so they're probably, the impact is probably less. Okay, so I've been talking about WebVPN, SSL. So let's talk about some protocols that we're going to need to understand for the vulnerability. So I said originally I found the bug in SSL VPN. So SSL VPN is basically what you're going to see if you use AnyConnect clients. If you use an AnyConnect client either on your phone or on Windows or whatever, this one is on the phone on the bottom right. It's going to establish an SSL VPN connection. It's basically SSL. And on the left side, you have the web browser, which is a clientless version of the same protocol. Then you have IKE. So IKE, originally, when I found the bug, IKE wasn't, I didn't find the bug in IKE, but I've used IKE to help me messaging the heap and exploiting the bug to prove remote code execution. So originally, it's just a helper, even though now we know it's also exploitable potentially over IKE. I'm not going to talk about that today. IKE can be either IKEv1 or IKEv2, and is mostly used for like static point-to-point VPN between two gateways or firewalls. But it could also be used by AnyConnect or a Windows client, even though I've never been able to configure it. So some previous work. There hasn't been much research on ASA, but there are a few very interesting research to start with. In 2014, so it's almost 4 years ago, Alex Stewart presented, I think, a very original research on how to root Cisco ASA and how to leak the version remotely. So it was like a very good presentation with like Mario Adventure, which is quite nice slide to read. In 2016, Exodus Intel published a really nice exploit in the IKE Cisco fragmentation payload, where basically they exploited a heap overflow. They got a CVE, they responsibly disclosed it to Cisco before talking about it. It was well done. Very nice bug. They published proof of concept, like an exploit for a specific version. Very good starting point to understand the internals. And then, interestingly, 6 months later, the shadow brokers leaked lots of files targeting routers and Cisco ASAs, and there is like a SNMP Stack Overflow targeting all ASAs since ages, targeting from version 8 to 9, and quite crazy. And because there is no stack cookie, Stack Overflow, at that time there was no NX, ASLR, Stack Overflow, return on the, on the stack, shellcode, win. So that was pretty nice. So that was basically the base of our research. We saw that, and because I'm basically, one of my job is to weaponize exploits so we can show the vulnerability to clients, basically weaponizing these two exploits so we can use them when we need. And then to actually weaponize all these exploits, I actually needed to build some tools. I mean, some people are really good. I don't know how Exodus Intel actually managed to exploit this bug, but if you don't have any tool, like what we saw in the previous presentation, tools really help understanding how things are going. You need to some helpers. So I ended up, just for this, working on a bunch of tools to help me. And with a colleague, we released a series of 8 blog posts with different tools and internals we figured out. So if you want to have a look later. So we also released these tools last summer. And so we named them ASA tools, and it's basically 6 tools. The first one is ASA firmware. It allows you to unpack and repack the firmware because it's like a binary format. And it allows you to inject a GDB server or unpack the firmware to actually mine the firmware, understand what mitigation is in there and whatever, because you have like 200 different firmware. So if you want to know which one has a latest mitigation, for instance. And then we have ASA DBG, ASA debugger, which is not really a full debugger in that we don't implement the whole debugging stack because we rely on GDB. But it's basically a wrapper on top of GDB that allows you to connect to the GDB server and have a nice interface. And we also support both QEMU debugging and the real hardware. The real hardware, you have the serial line, so you can debug over the serial line instead of having your Cisco shell if you're local. The other thing we ended up doing is basically building tools to analyze heap structures. They support, depending on the version, either DLmalloc or ptmalloc. So we ended up writing tools to display the heap so we could analyze the heap feng shui and structures in memory. And we also wrote a tool to analyze the mempool structures. So they are actually internal metadata specific to Cisco that are embedded into the DLmalloc or ptmalloc metadata, and that contains actually useful information. We'll see later, but like the actual caller that did the allocation, which is quite nice when you do some feng shui to see which chunk has been allocated by what function. And we also use RedSync, which is basically a very nice tool developed by Alex Gaze, which allows you to synchronize IDA and a debugger. If you use IDA and a debugger very often and you need to synchronize them, or instead of copying things from one to the other, which I used to do that, it's very nice. And I will show you in a demo how we use that. And then we also wrote IDA Hunt, which is kind of a small tool in that it allows you to run IDA from the command line, but just spawning like 10 instances at the same time, and so you don't have 10 instances of the GUI of IDA running, but it allowed us basically to run IDA on different firmware, 200 of them, and in order to mine information and execute IDA Python scripts. So it's not related to Cisco, it could be used for other stuff, but we used it for Cisco. And we wrote a tutorial like on our repo, which allows you to set up your ASA from scratch, like installing GNS3 and having it QEMU enabling GDB and debugging, basically, and then having it working. So this is basically what we have. So this is a quick demo to show you the debugging environment that we use to basically weaponize the exploit and then actually exploit the bug I'm going to talk about today. So on the left side, yeah, right. So imagine that we're attached to an ASA, like we're already attached, and on the right you have GDB client, which basically is connected to the GDB server on the actual router. And on the left side, you have IDA, which is synchronized with GDB with the two plugins. On the bottom right, we have a script that we're going to run to talk IKE. The idea is we're going to trigger some breakpoints on the debugger. So we send different packets, and now it triggers a breakpoint. So maybe you saw on the right IDA change color. So now we're using a DL chunk with a command to show the different chunks, and we can see on the right we have the actual symbols. What is interesting, we don't actually have the symbols in GDB, but we are basically fetching them from IDA. So here I'm showing that we have some data that we analyze in the actual content of the chunks. And if we do a regular backtrace, we don't have the symbols, but if you do the beautiful backtrace that we implemented, we're fetching the symbols in IDA, and we have this trace. So it's a lot easier to debug. And if we step by step, it's going to step in the graph of IDA. So this tool works for other debugger. I didn't write it. It's Alex Gaze, but I mean, this tool helped me working with ASA. Okay, so I want to clarify one thing about Cisco ASA, which is the system of branches. Because when I started with ASAs, for me, it was a nightmare. I didn't understand anything. I didn't know anything about ASAs. And the system of branch is, at least to me, it was completely not intuitive. You have different versions, okay? 7, 8, 9, 1, 9, 2, 9, 3, 9, 4, and 9. And actually, they are actually branches in the term of they are living together, and think about them as Windows XP, Windows 7, Windows 8, Windows 10, basically. So they have different mitigations, like Windows, and they live together. And some of them are end of life. So that's interesting. It's not intuitive because they are just numbers, I think, and some of them are still patched. Okay, so if you're on the 9.0, your end of life, you're not going to have the latest patch. If you're 9.1, you're patched, but if you're 9.3, you're end of life as well. So avoid 9.3, 9.5, but stick on the other one. But interestingly as well, you have this kind of thing for different bugs. You'll have different versions that you need to be aware of to actually have the actual patch for the branch you're interested in. It's not about having the highest number, it's about having the right one on your branch. And actually, I wouldn't recommend all the one in yellow. The reason why is because version above 9.5.1 only have ASLR. So we're able to basically mine all the mitigations by using ASA firmware tool that we brought. And also some version below 9.3 or 9.4.3, depending on the branch, don't have NX. So you end up actually, if you really want the latest mitigation, you want to be above 9.6, 9.3, well, 9.3.2, but because of the latest bug I found, you want to be on the 9.6 branch now. So ASLR and NX is enabled after 9.5.3. Right. So the last thing to discuss is basically what we're going to talk about today. The exploit I'm going to show you only works at the moment on dlmalloc without NX and without ASLR. So it shows one thing is that even though there is like a known method to exploit the bug, if you stick on on the latest version, you raise the bar and it's a lot harder because basically you need to leak ASLR remotely, like what Eternal Blue or Eternal Romance actually need to do, which is a harder problem. I'm not saying it's impossible. I'm just saying it raised the bar, definitely. So the bug is not in IKEv1. The bug, I exploited in WebVPN, so it crashed in WebVPN, and I'm using IKEv1 to massage the heap and get remote code execution. So earlier, the title of the presentation is Robin Hood against Cisco ASAs. Why Robin Hood? So originally, I was like, okay, I need to leverage iKey to exploit the bug. And interestingly, some really old devices only have 50 iKey sessions available. And if you want to massage the heap, it's a constraint because you cannot send as many packets as you want. But if you have like a more expensive device, you're gonna be able to create more sessions. So why am I saying you can only send less packets? Is because basically I'm gonna leverage iKey fragmentation. And iKey fragmentation, you have a limit of 8,000 bytes per session. And so the more sessions you have, the more feng shui, the exploit is gonna be more reliable on these devices that are more expensive. And I found it cool, like, oh, it's actually possible to exploit like the big giants with like really expensive devices that have lots of sessions because it's gonna be more reliable. And basically with my exploit, I'm gonna basically be able to rob from the rich and give to the poor. So I'm like, okay. Let's call it Robin Hood. So anyway, so I haven't talked about the exploit yet, anything. So let's get started. How did I find the bug? So originally, I wanted to do some fuzzing, and I was like, we have AnyConnect, which is nice because it allows you to establish an SSL connection, and it's pre-auth, okay? I'm just gonna look at the message pre-auth. So I used burp, and I sniffed the first message, and I ended up with an XML packet, which has a bunch of fields, like the version of the client, but all we're interested in at the moment is XML. Doing some kind of reverse engineering, starting from the existing XML tags I found, and ended up finding this huge table, which contains 20, well, not huge, but 27 tags. So that's not many, but what I ended up doing is basically writing a template with my 27 tags as an initial sample, and I wanted to do some mutation fuzzing. My fuzzing architecture is really basic. I don't do anything like concurrent execution or even code coverage or whatever. I'm remote. I have the router. From my PC, I send a mutated packet using my initial sample and using Radamza. It's quite nice for XML because it's going to generate valid XML kind of still. And I don't care about the response, the reply, but then I do an ICMP ping to see if the device is still alive, and if it died, it's going to reboot. But all it matters is I don't get any reply from my ICMP packet, so I know the packet I just sent was interesting because it crashed the router. It's really slow. I don't attach any debugger. I don't need it at the moment. And wanted to start the fuzzing before going on leave, and the ASA kept crashing. So that was good and bad. The good thing is I already found a bug. The bad thing is I couldn't leave the fuzzer during my holidays because it would fill my hard disk. So anyway, I went on leave, and on my way back, I was like, okay, I need to understand what's going on. So let's understand the bug. So the first thing to know is, because we wrote this ASA DBG instrumentation tool, which allows you to attach GDB, restart the device, attach GDB, restart the device, we are going to leverage our ASA debugger tool to automate triaging the different crashes, just to know if they are the same. We assume they are all the same crash, but it would be nice to be sure. So we do that. We connect GDB, fire the test case, save the crash info, and so on. And we use something like that, a basic GDB script, which basically define a hook stop, which will be called when the debugger will hit a state and give a hand. And basically, all we do is we save the backtrace and the registers in a text file, and then we can basically have a wrapper that's going to go through all our text file and see if they are all the same crash. So yeah, so we got what we thought. They are all the same crash, which makes sense. So here you have a screenshot of the actual instance. It's QEMU because I fuzzed it on both ASA and ASAV, which is the virtualized ASA in QEMU, and I tested it on both 64 and 32 bits. So it was interesting to find the same bug. So from that, you know they are all the same crash. You take the smallest sample, so you have something like that, which has a bunch of XML tags, and basically I ended up manually removing tags to see which one was interesting or if there was anything interesting. Could have automated it, but I tried manually first, and it ended up being quite quick, so that's why I didn't automate it. So, and that's what I got. So it's basically a config auth, which is basically the wrapper, like the thing you need to send, so it accepts your XML packet. But the interesting bit is the host scan reply, which is the tag that if I remove this tag, it doesn't crash anymore. So it's due to this tag. And the other interesting thing is I actually need to send the packet twice to trigger the crash, which I was quite lucky to find it by fuzzing, but it's basically, I found it because at some point I sent it twice. So I attach a debugger, look at the backtrace. I'm in a free call. So at the moment, we don't know if it's like a heap, use after free, heap overflow, double free. And we can check that you have two interesting functions. One of them is related to the processing of the client, and it's in a parser function. So it's definitely related to our XML packet. So now, basically, we have a starting point. We look from the backtrace, we look at the different functions that are around that. And after 2 days of reversing, and we end up with some understanding of what is the bug. So we have aggregate auth parse buff, which is basically responsible to parse the XML. And the way it parses XML is going to initialize a libexpat, which is an open source library, and they rely on that. And the way, if you want to use libexpat, you need to define some callbacks that's going to be called by libexpat each time some XML tag or data is encountered. So basically, the way it's implemented in ASA is you register auth start handler when a tag is open, and you have auth data handler, which is for when data is parsed by the libexpat, and you have end handler, which is for when the actual tag is closed. And the interesting thing is I found the bug in the actual data handler, meaning when the actual data for the actual host scan reply is parsed, so in this case, A. So I wrote some pseudocode that from my reversing, but basically I have different steps, like 1, 2, 3, 4 in the actual function parsing the data, and then I have step 5 in the actual function, another function that actually frees some kind of pointer. So I'm going to use some animation just to explain it to you if you don't want to look at the code, but just to understand the problem. Otherwise, you can follow with the code as well. So when the first so remember, I sent 2 XML packets. So the first packet I send, basically what it's going to do in step 1 is going to get, because it's a host scan reply, it's going to get the pointer from alloc, which is a specific case. And we can see there is a specific case for the host scan reply tag. So it's going to allocate a chunk in step 4. And the reason why is because there wasn't any pointer before, there wasn't data. Step 2 and 3 are going to be skipped. And at step 4, it's going to be allocated. So now pdata is hold our pointer to our allocated chunk, and we set it to alloc for later. And later, so some data is copied into the chunk, and later, in step 5, we end up freeing the chunk. So we have a free chunk, but actually one problem is there is a dangling pointer to this region, but it's in a free chunk. So now we send our second XML packet, and again, we go through the steps. Step 1, we get the pointer. Step 2, we check if there is some data. And we check if the pointer is valid. It's valid because there is a dangling pointer. Check if there is data. There is, because it's a free chunk. It holds some metadata in the free chunk. And then we check step 3 if there is some previous length. Yes, there is, because there was some data. And we end up calling string cat to append the data into this free chunk. And then we return. So we don't reallocate anything. We just append some data in the free chunk. But what is really interesting is later in step 5, we're freeing a free chunk again, resulting into a double free. So now we know it's a double free. And what is interesting is we know it's a double free, but also for 2,000 bytes, because the malloc is 2,000 bytes. So here we don't overflow any memory, like 2,000 bytes, the check. I don't show it in the actual code. The 2,000 bytes is fine. They check the size, but it's just, we have a constraint with the double free. It operates on the 2,000 byte chunk. So just how our further found it, because there is inline metadata for allocated chunk and free chunk, but they are different. Basically, when you free a chunk, there is some check on the metadata that is actually a valid allocated chunk. And because we do a double free, the metadata is wrong, and it ends up resulting into an assert. Hence, why our further found the bug. Okay, so we have our bug. We know it's a double free. How do we exploit that? I ended up using a technique because I've been working on iKey, and I know it's quite nice to do some heap feng shui and leverage interesting structures in memory. I ended up using iKey. So let's do that, and let's do it like Robinhood, using as many sessions as we can. But our ultimate goal, before getting remote code execution, is to trigger some mirror writes. So I call mirror writes a special write primitive due to double linked list pointers. The idea is in red you have, the example is an allocated chunk, and so you have the dlmalloc header, which is pref, foot, and head, and underneath you have the actual mempool header, which is specific to Cisco. And for Cisco chunks, you have a special double linked list for allocated chunk. So if you've done some heap exploitation, usually you have double linked list for free chunks, like for free list. But here we are actually talking about allocated chunks. The idea is they can track allocations to know who, like what stack, is it iKey that is taking lots of memory, or is it SSL, so they can track who allocated what. And so what, from an exploitation point of view, these pointers are really interesting because we can, if we can corrupt them, when an allocated chunk is going to be freed, this chunk is going to be removed from the double linked list, and we can potentially get a mirror write primitive. We call it mirror because they're going to be two operations, two write operations, and one of them is going to be useful, and the other one is going to be a side effect. The interesting thing is this actually was exploited already by Exodus Intel in 2016, and it's possible because there is no siphon linking, and we were able to abuse it still. The other thing to know is that even though the dlmalloc or ptmalloc would have siphon linking, the Cisco mempool doesn't have siphon linking. So our strategy, just to, before we go through the different steps, is we want to massage the heap to do some feng shui. We want to leverage our double free primitive. We're going to see that we call actually repeatable free primitive. And then we want to basically corrupt some data on the heap in order to create a confusion state and then overflow some memory in order to overwrite the pointers that we want the mirror write primitives of. So it's quite like a complicated process. So I'm going to explain how basically to work from nothing, no primitive, and basically build primitives one on top of the other. So first, if you're not familiar with iKey reassembly, basically the idea is a little bit what was explained in the previous talk is you send different I-key fragments, and they're going to be reassembled into another packet. And here the idea is you send sequence number 1, sequence number 2, sequence number 3, and the last one has a special bit indicating it's the last one, and that's when it's going to be reassembled. And this was used to exploit the bug by Exodus Intel because the bug was in the I-key reassembly. But actually, the I-key reassembly is a nice primitive if you can corrupt things, because we can. I'll show you why it's interesting. But basically, what we learned from the previous bug is that I-key fragmentation is also a nice, reliable feng shui mechanism. I'll show you right after. And that the reassembled packet length, which is used for when you actually receive the last frag, to actually allocate the packet to hold the different fragments, it's updated each time it receives the fragment. So let's say we receive the first fragment. You're going to have somewhere, it's going to store the length of the first fragment. And then we receive the second one, it's going to add that to the length. And then the third one is going to add that to the length. And now it's allocating the reassembled packets, but it doesn't check the previous length for the fragment. It's just using the one it has computed, right? And we're going to see that if we are able to change the length of one fragment before we trigger reassembly, we can potentially do something wrong because the reassemble length is going to be trusted. But anyway, the normal way is basically to copy all the fragments and everything is fine. So the other constraint we have with I-key, I said earlier, is we can't send more than 8,000 bytes per session. And this can be annoying because we have another constraint on the actual XML buffer, which is our double-free bug, which we're gonna call repeatable free just after. But basically, because it's on a 2,000 bytes chunk, if we do a heap feng shui just on 2,000 bytes, we end up we want to spray send lots of 2,000 bytes packets to fill all the hole and have our deterministic layout, but we can only send 4 per session. So you need lots of sessions to actually massage the heap, right? And the other thing is, it also limits how many mirror writes we get, because our ultimate goal, we're gonna show that, but if we work out with 2,000 bytes chunk with a feng shui, and we have an overlapping, at some point we get a hole, and our goal is to corrupt some target chunk, we're not going to be able to corrupt many of them because we need to replace this overlapping chunk with an I-key fragment, which needs to be less than 8,000 bytes, which is the maximum. So our solution at the end, which I'm going to explain, is to use 800 bytes, because 800 bytes times 4 gives 2,000 bytes. So we have we've just changed the granularity. Okay, so let's build our primitives. So first primitive we want is to create holes. So we're going to use 2 sessions. The first one is going to basically be used to send different fragments to fill all the hole, and at some point we're going to have some adjacency. So everything I show you is I-key fragments, right? And at some point when we have some adjacency, we can send another fragment from a different session. So I'm using different colors to show you different sessions. And then I can just have another fragment after, just so my session 2 fragment is in between. And now basically what I'm going to do is I'm going to trigger reassembly for the session number 2 in red. And the idea is, because it received the last frag, the idea is it's going to actually trigger reassembly because it's gonna think it needs to reassemble them all, and it's going to copy my 2 fragments into my reassembled packets. And so it's going to fail because I didn't send any valid I-key packet at the end in the actual data. But what matters here is that we created a hole because the actual fragment itself is not needed anymore, and it's going to be freed. So we end up having a hole controlled in the middle of packet we send and know are going to stay in memory. So I'm using the dot square to show a free chunk. So we are able to, our first primitive is to create a hole. We can create a hole. The second thing we actually need to do, which I didn't do at first, but I ended up doing it because it would improve my feng shui, is basically every time later when we're gonna want to work with like our 800 bytes chunk to do our feng shui, lots of small allocations end up being made in addition to our 800 bytes, and to avoid having them mess up with our feng shui, because what we want basically, the first line is the different fragments, 800, all next to each other, but we end up having some small allocation, like in the second line in blue, that end up being in the middle and that mess up with our feng shui. We want to avoid them. So what we end up doing basically is to previously create a small hole. So next time we send our fragment, the small blue chunk will go into our holes and we'll get the adjacency we want on top. So basically, how do we create hole? But we just use the same technique as we explained before. So initially we send 70 bytes fragment chunk in 2 different sessions, and we just alternate the packets. And at some point, we just reassemble session number 2, and we get lots of small holes. And that's enough. Next time we want to send our 800 bytes chunks, all the small blue chunks will go inside the small holes, and we'll get adjacency with our black fragments. So from now on, we can get some adjacency for our fragments. So the primitive number 2 that we have is basically the one due to the bug. So it's a double free vulnerability, but actually this primitive is a lot more powerful than a double free primitive. And it's actually funny because it's similar to the bug that was presented earlier. We can call it several times because I said earlier, we can send a different packet to trigger a free. And if we reallocate something in between, we can actually free it and then reallocate, free it. So it's like a good, very, very, very strong primitive. So let's say we have our hole. We have our 2000 byte hole. We send our XML packet. It's allocated into our hole. But we know it's going to be freed. There is a dangling pointer. Now we send a fragment for a session, okay? For now, we leave a free hole. I'll explain why later. But basically, the idea is the session fragment and the dangling pointer point to the same memory region. Now we send our second XML packet, and it's going to trigger our repeatable free primitive. It's going to free our actual IKEY packets. And now what we can do is send another fragment from another session and confuse our initial pink fragment with a purple different fragment. So now we have an interesting state, right? We have a confused state, or a confused fragment, the pink one. So that's basically what we have. So I'm showing basically the output of DL chunk, and it shows you on top you have the actual pink one, which is the initial fragment that we send before freeing it, and we can see on top that it's allocated because it's M for malloc, and then underneath we have a free chunk of 10 bytes, and we can, if we print the actual content of the chunk, we can see that the payload length of the IKEY header is 1FE6. And later, we do our repeatable free, we reallocate a different chunk from a different session, and now we can see we replaced it with a payload length of 1FF2. And basically what happens is we confuse the pink session fragment and we increase its length. Because of the alignment, we just overrode the memory with a different length. And in memory, it thinks the payload length is different. So the trick really here is really to leave a small fragment, a small free chunk after S1, and we get our confused payload length. So this is our third primitive, confused fragment length, that we get from the repeatable free primitive from the previous one. Our fourth primitive is actually similar to what Exodus Intel did to overflow IKEY v1. So even though now all the bugs that they found are patched, we're gonna actually use a trick which is quite similar. The idea is basically to abuse the previous primitive where we change the length of a fragment to actually overflow some memory when we reassemble the packet. So again, the reassembly, the normal one is to send different fragments and reassemble them into the actual reassembled packet. But in our case, what we want to do is basically send our fragment like the normal way, okay? It's going to update the reassemble length in memory. And now that the length is computed, basically what we want is we want to increase the length of one of the fragments. And what's going to happen is it's going to reassemble the packet with a fixed size, which capital N is N plus P. But then it's going to copy the different fragments, but one of them is larger, and we end up overflowing some memory on the heap and doing a heap overflow. So that's our fourth primitive, which is overflowing the heap. What is interesting is actually there is a check when they actually copy the different fragments, like when they actually copy the fragment, they check that it doesn't overflow the reassemble length, but the check is incomplete because of some alignment and the structure that they take into account that they shouldn't have done. We end up having this capability to actually overflow up to 18 bytes. So that's good enough for us. We are able to corrupt some adjacent memory. Okay. So I'm going to do a demo, going to try to exploit this ASA 5505 that only has 25 IKEY sessions live. I do have a video if it doesn't work. It's not 100% reliable, but before I'm just going to show you the different steps to summarize. So the idea is we want to use different IKEY1 session, okay? So on the right, on the top right side, we're going to have the different sessions with different colors to say that they are part of different sessions. On the bottom left, we have, on the bottom right, we have the heap, different things going on the heap, somewhere on the heap. And on the bottom left, we have somewhere where we have some adjacency. That's where we're doing our feng shui. So we send a bunch of IKEY fragments, which are to fill all the hole in blue. And then we send different fragments adjacent, because we filled all the hole, that's going to be allocated that are part of the same session. So I'm using green to indicate a session that's going to be used later to create a hole. And here I'm using 4 of them because 4 times 800 gives 2,000 bytes, which is the size of the repeatable free primitive. So I want to create later 2,000 bytes. But for now, I'm just sending different fragments that's going to be adjacent on the heap. And here I'm sending from another whole creation session, like another green, not the same as the J1, but with like 5 of them. We're gonna see why. And basically the K1 is gonna be used for the reassembled packets. And because it's gonna be used for the reassembled packet, and we're gonna overflow some memory, then we send different fragments. That's gonna be basically our fragment that we target to corrupt the linked list pointers to trigger our mirror writes. Okay, so we have this layout, and because we want to check that it works, we use DL chunk to show that we have the layout we want. So if you don't want to follow the actual tool, I'm going to show at some point the output that our tool shows us so we can debug the actual feng shui. But basically, this is quite handy, I mean, at least I think, to show that our feng shui works and we have the actual layout that we're expecting. I'm using -P to indicate that it's going to show the actual content of the chunk, and that's why we see the IIJJ, because we're actually showing the actual content of the actual chunk. So now we are going to do our exploits. So we send our last fragment for the J session, and it's going to basically reassemble the J session. It's going to create a 2,000 byte chunk, which is free because reassembly occurred. So we can see in bold, it's a free 2,000 byte chunk. And now we're sending our XML packet. It's going to fill the hole because it fits the size. And now it's going to free the chunk as well due to the free at the end of the handling. Now we send our first fragment into a different session, and that's going to be the one we want to corrupt. It has a free chunk after, because it's smaller than the actual chunk, and then we trigger our repeatable free primitive to free the actual fragment that we just send. So we see it's freed now, and what we do is we send our replacement fragment to overwrite the previous fragment, and we've corrupted the actual session fragment, and this is the payload length I showed earlier. So now we basically corrupted the length of S1 with like the actual length of S2, so it's increased. And now what we want is trigger reassembly of the session 1, but we need to create a hole first. So we reassemble the K session, which is 2,800 bytes, and it's going to basically create a 2,800 byte hole. So now what we do is we reassemble the session number 1, and because we increased the size of one of the chunks, the actual buffer that's going to be reassembled, that's going to be smaller than what's going to be actually copied. So we're going to end up allocating a we're going to end up allocating a buffer which is smaller than what we're going to copy, and we end up being able to corrupt the free chunk which is right after, and basically increase its size from 30 bytes to whatever we want, because we control the data we want that we use to corrupt this chunk. So now basically what we have is we have a free chunk which was increased in size, and because the reassembled packet is going to be freed because it's not valid data, they are going to be coalesced together, like the one in pink and the adjacent free chunk. So we end up having 2,800 plus 2,000, and we end up having 4,800 bytes, which basically encompass the following chunk. And basically here we win, because we can replace this hole with like control data from another IKEA sessions, hence the Robin Hood technique. But basically we corrupt all the adjacent chunks, and we corrupt all the maple header and all the linked list pointers, and we can basically have a mirror write primitive from now on. So let's get our mirror writes. We send the last fragment to reassemble the different session. So reassemble the P session. It's going to trigger the first mirror write. So the first thing we do is we disable check heaps. The reason we disable check heaps is because there is a mechanism that checks the heap, and disabling it allows us just to make sure it's not going to stop us from the exploits and just reboot the router. Then we send 3 of them, and the idea is to actually write a trampoline somewhere in memory to give us a way to execute some kind of shell code. And the last one we use, basically, it's to overwrite a function pointer that's going to be used the next time you want to initiate an IKEA session, because then we can basically send a IKEA session and get a code exec. So the idea is we curve this function pointer, and now we can send our IKEA init packet. It's going to basically go through the parsing through this function, but we patched it. So we're going to basically go through our trampoline, and now basically it's going to, with a bunch of dereferencement, to basically jump to our packet and execute our packet. And we win. So I have a demo. So on the right, I have both are the attacker. I'm remote, and basically, so I'm checking the router is alive. And now I'm going to trigger the exploit. And on the right, I have a shell waiting for me to connect, and I have a shell. So I'm not going to talk about that, but before actually working this way, I tried a bunch of other techniques which didn't work, which I documented in the slide if you're interested in. But basically, the interesting thing is it took me basically 2 weeks to actually build the exploits. But obviously, it took me months before to actually write the tools that helped me understanding the layout and stuff before. So just as a conclusion, what do we learn from that? So the interesting thing is, at first, I was trying to do some fuzzing, but actually, I find it a little bit lame to call it fuzzing because it was just sending the actual tag that it was supported would have been enough to actually find the bug. So in our case, Radamza was useless. The exploit currently works on 32-bit. It would be easy to port on 64-bit for the same versions that don't have NX and ASLR. The challenge is more complicated with ASLR because you need to remotely bypass ASLR, even though I have some ideas. It's a 7-year-old bug. I don't know what you think, but for me, it means nobody looked at it because I was quite lucky to actually find this bug by just trying things. And one thing I learned from it is that IKV1 is really powerful in order to leverage interesting states on the heap and to do some feng shui. Even though it's not 100% reliable, it works quite nice, especially that Cisco ASA, if it crashes, basically it's going to reboot, and then you get basically a fresh state where you know it's going to work like 99.99%. So, like I said, I've used WebVPN for the actual bug, but I've used IKV1 for the feng shui. So it would be nice to see if it's possible to actually exploit it just using WebVPN only. And now that Cisco told that there are other attack vectors, actually having it working just on IKV2 would be maybe good. And the last thing is, for the next steps, is basically this repeatable free primitive is very powerful because we can call it several times, and a little bit like what the ZDI guys did before. It would be nice to use this repeatable free to basically get a leak back and bypass ASLR remotely. And maybe find other bugs like using real fuzzing. So just, if you want to protect against 0 days, or if you just want to advise your clients what to use, just use the one in green. Just stick on the version with ASLR NX. This one. Make sure you're patched to this bug if you want. And yeah, I want to thank my colleague who helped developing the tools, Cisco Cert for handling this, and lots of people for providing feedbacks for my previous presentation so I could improve it for this one. And thank you very much. If you have any questions. Not sure we have much time for questions, by the way.
Anyone? No? Okay, I have a question. Yeah? My question is, first of all, we know that Cisco doesn't do bug bounty.
No, they don't.
And we know that the bugs that we probably cannot sell to Zerodium, do we know the price? Or do they even buy Cisco's bugs?
I would be interested to know. I don't know.
And I think the answer is no, they don't buy either. So
I don't think they buy it,
yes,
but I don't know.
Yeah, okay, that's all right. Maybe they do, maybe they don't. Yeah. So the question is, if they don't buy, and Cisco doesn't do bug bounty, and we are at an OffensiveCon, as to what I see, the only outcome to us finding these bugs is so that we can have a better infrastructure and like for the general well-being of humanity. Is there any other objective to finding bugs in a Cisco IOS?
You mean for me, or you mean
or
for people in general?
For us, like.
Well, I think having access to the infrastructure of people can be interesting for some people.
Okay, thank you, that answers.